Hi, welcome to this lecture on hash tables. My name is Dr. Ritesh Ajuda. In the last lecture, we spoke about maps. If you haven't watched that video, I invite you to do so because you are going to need the knowledge from those lecture slides in order to understand the content in this one. So just for those who have watched it and are a bit fuzzy on what a map is, we remember that a map is a searchable collection, which means that it stores key value pairs, and there were certain methods associated with them. I won't go into them in detail because I do explain it in the last lecture. So there's find k, which looks for k. K is the key. Put kv, which takes a kv pair and searches in the collection if the k exists already. If it doesn't, it adds it to the map. Erase k, which removes k, but first we need to find k, so we search the collection. And in order to search it, we require O(n) time, complexity in the worst case. Then we needed another method called size, which kept track of a counter. Every time we put an item into the searchable collection, we increment our counter. And every time we erase something from our searchable collection, we decrement the counter, which gives us a constant, or a value, some kind of numeric integer that we return whenever we call size. If that is a non-zero value, then our empty will be false. It means it won't be empty. There are things in there. If it is a 0, then our empty will be true. There's also entry set, which returns a list of all of the entries. That's a new one. I didn't speak about that before. And then there's also key set, which returns a list of all of the keys. But my point is that a map is a searchable collection. There are certain methods associated with it. There's ways of adding things to it and removing things from it. And this is what makes it a map. We spoke about the applications of maps as well. And these included things like address books, the list of users of a workstation or computer, Facebook's large repository of people who use it, and also all of the Amazon accounts. So there's many ways, many different applications of using maps, many different applications of maps. But obviously, the way you implement a map depends on the application. If we have a lot of erasers in our map, we require a particular implementation which provides the ease of computational complexity in using that. If we have lots of puts, we want a way that's efficient on puts. It might not be efficient on erasers, but because we're using put more frequently, it needs to be efficient on puts. Finds, if finds are even being used at all, maybe it's so rare it never happens. These need to be considered when implementing a hash table, and you will find every time I speak about hash tables of ways of implementing them, it is always dependent on the application, always. And we can't be too certain about anything because depending on what will be used for, there are different ways of choosing the components of. In this lecture, we'll speak about hash tables, the different components of a hash table, the hash value, the hash code, the ways of distributing the integers. All of the different methods of doing this depend on the application, and this is the first one. This is the most uncertain lecture in terms of being very sure about what to be used, what methods to be used, and when. We can't be sure of ourselves here. When it comes to maps, we can't be sure of ourselves because we don't know what the application is. Different design choices provide different computational complexities, and this needs to be considered when putting this together. And this is why we have this course, Data Structures and Algorithms, because the programmer or the computer scientist, which you are now, needs to select the best ways to design their procedure using various algorithms, using various data structures in order to provide efficient search time, efficient insertion time, efficient deletion time, whatever the case might be. So this is what you're here for. The human, which is you, is going to have to make these decisions when designing the hash table or whatever map that we're going to do. So one way of designing a map is using hash tables. We spoke about implementing a map using a linked list, using an array. But today, in this lecture, we will talk about hash tables. So what are hash tables? Well, a hash table it's a searchable collection of key value pairs. But the way it stores this is it uses something called a hash function, and it uses an array. And it has to, in this case, it has to be an array. So let's start with the hash function. So in this case, we denote our hash function as h. So the hash function h maps keys of a given type to integers in a fixed interval. Okay, so why is it a fixed interval? This is our array size. So our array, remember, we want to store items somewhere. We're going to store it in an array. And this hash function tells us where to put it. So it needs to map the keys. Remember our key value pairs, KV. It needs to map this key to a position in the array. That's what the hash function does. So it maps the key somehow with some mathematical function. It maps the key to the array, the index in the array. And in this case, like I said, it has to be an array. So here's an example of a hash function. This is a hash function h of x. It maps a key x mod n is the size of the array. And whatever, if this is 66, if the key is 66 and n is 10, it'll be 6. So it's at position 6. It'll have to go into position at index 6. This is just as an example. We'll look at more examples later on, but this is an example of a hash function. So the next thing to consider is the hash value. Well, the hash value is just this h of x. So it's the output here. So this is the function. This entire thing is the hash function. And this here is the hash value. So whatever it hashes to, that's the hash value. So that's whatever this integer h of x is. That brings us to a hash table. Now we have enough concepts to talk about a hash table. So a hash table is simply two things. Okay, it's the hash function, which is this hash function, and it's an array. And the array is of size n. And this is important. You need to know what n is, because your choice for n also affects the performance of the hash table. Your choice of the hash function affects the performance of the hash table. So I will not be telling you in this lecture what's a good choice for a hash function or what's a good choice for n. These all depend on the problem and on the nature, the type of keys. It depends on where these keys are coming from, of what the distribution of keys are, how frequent perhaps odd numbers to even numbers in terms of the keys. So these are all important in making a decision about the hash function, in making a decision about the array. And so I cannot certainly tell you this is the hash function you need to always use, or this is the array size you always need to use, this is the hash code you need to always use, and so on. I can't tell you that. But what we could do in this lecture, and what I will be doing here, is giving you strategies of thinking about these things. And all I would do is provide the strategies to you, and then with the hope that you can recognize when to use them when the time comes. That's the best I can do with this, because depending on the nature of the keys and so on, different implementations work. The best way, unfortunately, with hash functions, this is now threading into, it's very difficult to think about this distribution of keys. This is now threading into those much more complicated problems, and unfortunately, perhaps our human brains can't handle evaluating which procedure, which particular design choices are better than others. So the best way to actually assess one set of design choices to another would be to use empirical analysis. And this is now threading in Lab 4, and when we spoke about computational complexity, here we'd like to actually implement the different design choices as scenarios and then try to evaluate which gives us the best implementation. And we will look at implementations based on, well, looking at the number of collisions of keys and so on. And this will allow us to make a stronger choice. But we'll discuss this. So in this lecture, like I say, I can't tell you this is good and this is bad. All I can tell you is that these are a set of heuristics, different strategies, design choices, and you're going to have to pick them for yourself. Okay. So just to clarify what's on the slide, you've got a hash function, which is some kind of function that takes in a key and returns a value, and that value will be the position or the index. It returns an index. So yeah, it takes in you put that key in a function, and the hash value is returned as I, and I is where in the array does the key value pair go. That's what we did in this slide, just to clarify that. Okay, so here's some examples. Well, in America, there's something called a social security number. In South Africa, we call it a identification number or an ID number. And in this, a social security number looks like this. There's 3 digits, then a dash, then another 3 digits, then a dash, and then there's 4 digits. So what you could do is, if you got a set of social security numbers, your hash function in this case, I'll just say it in words, is to look at the last 4 digits, return the last 4 digits as the I that we're gonna be putting this in. So for this social security number 025-612-0001, our hash function will return the last 4 digits, which is 0001, and that's where it's going to go in the array. So your array is of size 10,000. All we're going to do is just return these, and this is going to tell you if it does 0003, it'll go in position 3. If it does 0006, it'll go in position 6. When I say position in this case, I'm referring to not the pointer, I'm referring to an integer value which indicates the index of the value. Okay, so this is an example. So here our choice for our hash function was to look at the last 4 digits. That's what our hash function returned, the last 4 digits. You can think of it as a modulo 10,000 or whatever the case might be. And your array is of size n, which in this case is 10,000. Okay, so here's your n, 10,000, and h of x returns the last 4 digits. So that's pretty important. So we chose our h of x, we chose our array size, and we got a hash table. So what's the problem with this? Well, perhaps we have 2 people whose last 4 digits end with the same thing. Okay, because it's I mean, it's bound to happen, right? That's why you have all of these other digits. Although each of these keys are unique, you are going to have a situation where the last 4 digits of 2 people are the same. Same with the ID number, stuff, the ID books. There's also the last 4 digits. The last 3 digits corresponds to a particular thing. Take the first few digits of a South African ID number. That's the I'll tell you what mine is. The 12-12-91. That means I was born on the 12th of December 1991. And that there were many other people also born on the 12th of December 91, and so they would have the first few those first few digits will be the same. So if our hash function was looking at those first 6 digits, we'd be in trouble because then we'd have many collisions. That's called a collision because they would be all hashing to the same place. But before we discuss collisions in more detail, let's break up this notion of a hash function. So I told you the hash function distributes the keys into an interval. But a hash function in itself, conceptually, can be broken up into 2 other ways. Now, in this course, I don't really break it up too much because you could go into more detail here, but as long as the concept gets passed over, I'm quite happy with that. So the hash function is made up of 2 parts. There's the hash code and there's the compression function. So the hash code takes the key and changes it into an integer. Okay, because remember your key can be anything as long as it maintains an ordering relationship, like we discussed before. Your key could be integers, it could be a string or whatever the case might be. But you've got to now change that key into a unique integer. That means there's a 1-to-1 mapping, right? You can't have a many-to-one relationship here. I don't know if you did that in number theory, but you can't have that relation here. You need to have a 1-to-1 mapping because for every unique key, you've got to have a unique integer. And there's another component of the hash function called the compression function. Now that takes the integer and puts it into this array within the width of the array, the length of the array. So the compression function is responsible for that. So conceptually, ideally, your hash function, h of x, is given as h1 and h2. h1 is your hash code, which transfers the key, converts the key to an integer value, and h2 takes that integer value and it's a compression function, which makes it a integer, which is the index of the array. So this is important. Now, our hash function, what what is the best hash function? The best hash function is one that uniformly distributes the keys into this range 0 to n minus 1. It uniformly, which means ideally there might not never, we can even perhaps conceptually show that there might never be a perfect hash function in very complicated cases, but ideally our hash function is one that can uniformly distribute the keys within this range. That means that each key can go into any position in the array with equal probability. That's important. That's the ideal situation. We might never be able to achieve it, but that's our goal. And now we've got to choose our hash code. We've got to choose the compression function that can get us towards this goal of uniformly distributing the keys with equal probability to the different cells in the array. And like I said before, it has to be an array, okay? Because the hash tables require the constant time to access items in the array. That's why it has to be an array. Okay, so that's an important concept. So let's look at the different hash codes. So we're looking at this first, and then we'll look at compression functions. So let's start with the hash codes. So hash codes, well, there's many ways of doing this. Okay, remember what a hash code does. It maps the key to the integer. So there's lots of ways of doing this. I'll just brush over them. You'll find many more online, even in the textbook. So you could just use the memory address of the key. The memory of the address of the key, wherever the key is in memory, you reinterpret that memory address by as an integer, because the memory addresses are integers. Remember that they all just dereferenced as integers. There's no real number memory addresses. It's all just integers. So you could reinterpret that memory address as an integer, and it's a good idea. It's been used. It's been used in certain cases. There's another way of doing it. You could reinterpret the bits of the key as an integer. So perhaps you can decompose the key somehow to maybe breaking it up by the tens and thousands and units and so on. As an integer cast. That's what we'll be doing for the most part in this in this course. We'll just say, okay, we're not going to have a hash code because the value 66 will be interpreted as the value 66. The value 7 will be interpreted as the value 7. The key 8 will be interpreted as the key 8, and so on. Yeah, okay. And then you can look at the component sum. Well, a component sum also, you could sum across the key to get a particular key. So maybe if you got like, this is just an example, 1, 1, 1, 1, 2, you can just say, well, adding 1, 1, 1, 1, that gives you 4, plus 2 is 6. That could be another way of doing it. A component sum. That brings up another kind of way of doing it, which is a polynomial accumulation. And this is a fairly simple concept. We pick a z. Z is some kind of integer. And we build a polynomial. We have to sum across. Now it looks like it's going to take a long time to do this. So you suppose you have that value that I said before, 1, 1, 1, 2. Then you would just say 1, all right, that'll be your A1. Then the other A0 will be 1, A1 will be 1, A2 will be 1, and then A3 will be 2 because it's 1, 1, 1, 2. We pick a Z, any Z will do, as long as it's a constant. And we put it into this formula and calculate it. Now, the more observant of you must be wondering, my God, Ritzo, why would you want to do that? Isn't it more computational time to calculate? Isn't this hash code a computational burden in itself? Because now we've got to calculate the powers of Z. And sum them across. Well, that is true, but thanks to this very clever guy called Horner, we can evaluate the polynomial in ON in linear time. And all he does, this Horner, a very clever mathematician, all he did was he just said you can use the previous term to compute the next one. And you can use the previous term to compute the next one. This is a very easy way of doing it, and you can evaluate it in ON. So there is ON is greater than O1, right? But it can be done. This also has its merits. Like I said to you at the beginning of this lecture, I can't tell you which of these, whether it's using the memory address, or integer cast, component sum, or polynomial accumulation. I can't tell you which is better. I can't. And that's the reason why we have different ones, different ways of doing this. I can't tell you which is better. It depends on the application. So going to the next part, let's go back, the compression function. Okay, remember the hash function is a hash code and a compression function. Going back to the compression function, well, there's many ways of doing it. People use this concept called MAD, and that's multiplication, addition, and division. The division here is the mod. So multiplication, addition, and division. And this allows us to compress. Well, there are other ways. I'm just using the modulo seems to be the easiest, and this is it seems to be the least computational wise. But there are other ways of actually performing that division. But the compression function, remember, what we're trying to do here is take that integer and put it into an array. So this notion of a modulo, which kind of just gives you the remainder, and the remainder is within a range, this kind of helps us, right? Because we want to be able to compress from a large range, perhaps an infinitely, a range of infinite size. I mean, you could have, there's no max, there's no min. That's the range of real numbers or integers, for example. We want to be able to bring it down. So the range of using a modulo allows us to do this. And so we usually use a modulo when performing compression, using in a compression function. Okay, sorry about that. The compression, remember, is a field in computer science, and it refers to other concepts like text compression and those kinds of things, which is not the same thing here. This is compression is in reducing the range. It's a different concept. Okay, so then now we've got a way of doing, we now know how to choose. We don't know how to choose it, but we know of ways of choosing hash codes, and we know of ways of choosing compression functions. But let's now talk about our social security instance where we had two people which hashed to the same place. So two individuals, like I said, you could have a social security number which ends with a 4, and there could be another one that also ends with a 4. So we need to consider what happens in this case. Okay, when this happens, it's called a collision. A collision, things are colliding. It gets two things come to the same place. It's colliding. And there's a picture of a car knocking another car. Okay, and this collision, because these two keys were mapped to the same, were hashed. Sorry, they provided the same hash value, so they were hashed to the same place. A collision occurred. Collisions occur when different elements are mapped to the same cell. Now, there are different ways of handling this. There's open addressing and closed addressing. Now, closed addressing, let's talk about that first. So, a type of closed addressing is separate chaining. Let each cell in the table point to a linked list. So, if you have a collision, in this case, we had a collision at 4. All we would do is simply have an extending list. And the list can be as long as it wants to be, as many collisions as there are. This list will go on for as many collisions that occur in this spot, and it will expand outwards. So what do we notice? Well, we're using more space than the array. Okay, the array was of size, in this case, size 5. We've got 3 items, but we are using space that does not exist in our array. Okay, it's going outwards. So we notice the computational complexity in this regard. I invite you to think about the complexity for insertion, the complexity for finding an item, if you're given the hash value. So it's a very simple concept, separate chaining, but this additional space is, it does provide a problem, because we have to make sure now we've got additional space so we can build these large links. So there has been other attempts at handling collisions, and a more popular attempt is to use something called closed addressing. But before we get there, I want you to think about, like I said, the computational complexity of separate chaining. So in separate chaining, if you want to, let's think about this conceptually. You can go through these algorithms on your own. They're very straightforward, but I'll just explain them in a different way. I'll explain them more conceptually. Okay, so suppose you wanted to add a new item here that also ends with a 0004. How do you do it? Well, the way you could do it is simply calculate the hash value. Now, the hash value in this case looks for the last 4 digits. In the last 4 digits of our new thing we want to insert, is 0004. So we know it goes into this array. So all we got to do is go to the fourth index because it ends with a 4, and we're going to put it in here. So far, the computational complexity has been 01 because accessing any cell in an array is constant time. So 01. But we still have all our work ahead of us because now we've got to append this new item into this hash table. So we've got to now go into this hash table, traverse this list, and append it to the end, which is quite a lot of work. And in the worst case, you could think of this chain being extremely long. So we're using a lot of space, and also we've got this ON that we've got to search through. If you want to delete something from the hash table, same concept. Okay, suppose you wanted to delete something that ended with 0001. All we've got to do is we find that the social security number goes through the hash function, and the hash value then returns you 0001 because it ended with a 0001. So our hash value is 0001. We simply go to our index 1, and we look into that cell because we know it would have been hashed to that position. So now we're erasing it. We then traverse the list. In the worst case, the list is very long, ON. But in the best case, we find it immediately. And then we simply delete it. So that's how you would, this is the same algorithm over here, erase, okay? So you first find the position where it hashed to, and then we simply remove it. We also need to decrement our size because we took something out. Same concept with put, right? It's you find the place where it hashes to, and then you put it in that position, appending it to that linked list structure. Don't forget to increment your size. And the same concept with find. So we notice here, well, hash tables are really great for using separate chaining because we can get to the position. We kind of know where to look. We know where to start looking. But the problem with separate chaining is that we still have this list to traverse. And this list takes extra space. That's a problem. So let's look at another way of handling collisions. This is called linear probing. Well, linear probing is actually a very popular way of doing this, and it still is. A lot of people use it. It's cutting edge. People have been using it for years, and it's a really good way of performing hash functions. A little tip for you: if you are interested in getting a programming job, you need to really know a developer job. Perhaps you want to be a developer for, I don't know, Facebook or Google or Amazon or whatever the case might be. Then getting a solid understanding of these concepts is very important because that's what they ask you in the interview. I digress. So in linear probing, this is what we call open addressing. It's a tactic of open addressing. Another would be, so there's linear probing, there's double hashing, a whole lot of them. These are all open addressing because now, before we were very much closed off. We closed addressing, closed as in we could only access our cell that we hashed to. So if you ended with a 00, if your social security ended with a 0004, it would be nowhere else in the table but at the index 4. It'll just be down this list. But with linear probing, you are allowed to access the other cells and store information in them. So let's see how it does this. So we have a collision. Okay, so the collision occurs, but we place it in a different cell on the same table. So we're not using auxiliary storage. We are using the storage that is provided by the table. And linear probing handles collisions by placing the collided item in the next circularly available. So why do we say circularly available? Because we are the next position from 11 is 12, and the position after 12 would be 0. After 0 would be 1, and so on. So circularly available as in we come back. And we're just simply adding it to the next contiguous position. All right, that's all there is to it. That's linear probing. Linear as in going to the next. So let's look at an example. Okay, here's our hash function. H of x is equal to x mod 13. we're inserting the keys 18, 41, 22, 44, 59, 32, 31, 73 in this order. Let's start with 18. So I've written it down here at the top for you, so you can have a look. 18 mod 13 is equal to 5. So you could use your calculator if you want, or you could just find out what the remainder is. If 13 divides 18, you'll have a remainder of 5. You could do long division if you like to, but I think it'll be better if you just take your calculator with. If it was mod 10, it would be easy, right? Because then you can just ignore the other digits, just look at the last digit. But it's not mod 10, it's mod 13. So that might be a bit difficult for some of you to compute. So carry a calculator with you when doing these kinds of problems. So you've got 18 mod 13, which gives us 5, which just means we're going to put 18 in position 5, in index 5. Here you go. Done. So we're going to put 18 here. 41, where does it go? 2. Right? 41 goes into 2. 22. 22 goes into 9. 22 is in 9. Okay. 44 goes into 5. But remember, 18 was in 5. So what do? Well, we can't put it on top of 18. So we just put it in the next circularly available cell, which means we'll put 44 in position 6. And we continue in this way. 59 mod 13 is 7. So 59 goes here. 32 mod 13 is 6. So we put 32 at position 6. But we can't, because 44 is there. Remember 44 hash to 5 and we put it in 6? Well, now we want to put something in 6, but we can't. So what do? We put it in the next available cell. So 32 needs to go in the next available cell. But we can't put it in 7, because remember 59 was hashed in 7. So we look in 8. And there's space. So we'll put 32 in 8. 31 mod 13 is 5. We go through the same story again. We can't put it in 5 because 18 was hashed to 5. 44 was hashed to 6. 59 was hashed to 7. 32 was hashed to 8. 22 was hashed to 9. And so 31 will have to go into 10. And finally 73 would hash to 8, which means that we would have to put it in this index, but we can't. 32 is there, so we go to the next one. 22 is there, we can't put it there. The next one, 31 is there, we can't put it in there. So 73 will have to go in 11. And that's linear probing in a nutshell. So yeah, this is how we can find items having hashed them using linear probing. Well, with finding items, it's not difficult. Here's an algorithm that shows you how to do it, but you just have to remember, all you've got to do is you find the hash value, h of k, you go to that value, and if you don't find it there, you simply probe, you look at consecutive locations until you find it. If you find it, that's fantastic. If you encounter a null, which means that it was an untouched cell, then you don't search anymore, because you know that the item is gone. On the other hand, the item is so that means that the item wasn't there. On the other hand, we could have had a situation where an item was removed, and so in that case, we do not replace the removed item with null. We replace it with a new kind of null called available. So we have these two kind of nulls in our stuff. There's the proper null, which means that the block was never it was never filled with anything. That's the null. And then we have another special a special character or special string called available. And available, remember, you could always just instead of saying available, you could always just put in a there, or a number that would never which wouldn't be one of your keys. But the point is that available replaces things that have been removed. And if you find available, then you know that an item was removed, and perhaps you can continue searching because you would have to probe the consecutive cells. So this is important. We need these two notions. Now null and our available. Now remember, you could do this in other ways as well. This is just a suggestion. You could do this in other ways. You could replace all of the item, every cell in the array with available, and then do it the other way around, which is a popular method. Or you could just, or you could do it the other way, where we have null everywhere and then just put available whenever you delete something. The slide tells you to do it the second way. I personally like to do it the first way. So it depends on you. You can actually do it any which way you want, as long as you're not doing unnecessary steps to blow up the computational complexity. Any way will do. As long as you understand why you're doing it, that's important. Okay, so that's linear probing. Recall that if you want to find something, all you got to do is hash to the value, look there. If you don't find it, then you continue to probe until you do. But if you do find it, that's fantastic. You stop looking. Right, now another kind of open addressing is called double hashing. And so before, using in linear probing, we would just look at the next cell. But now, instead of looking at the next cell, we will hash the hash value again to find a new cell to store the hash, to store the key. So, and in order to do this, we've got to be very clever about it, right? Double hashing uses a secondary hash function. So instead of h of k, let's call it d of k, and handles collisions by placing an item in the first available cell of the series. So when you double hash, the hash function has its own properties and its own design that allows us to not hash to the same place. It uses prime numbers for this. And it's also very clever in that it doesn't, if you hash infinitely many times, it'll try to traverse the entire array, obviously in a random way. And it won't always go to the same place. And it does this by using prime numbers. And it's a lot of stuff to go into. Like I said, hash tables, you can have a whole course on hash tables. But I just want to get you the basic concepts here, so we can, you can always learn about these things later on as the need arises. But for the sake of this course, it's important to know that the characteristics of this hash function are such that it doesn't allow for searching in the same place and redundant searches, stuff like this. It's very important that the hash function, the second hash function, is designed with the first in mind. Okay, so here's an example of double hashing. So suppose I gave you two hash functions. I gave you h of k, which is just k mod 13, because 13 is the size of the array. And I gave you another hash function, d of k, and this k is also a key, is equal to 7 minus k mod 7. And I asked you, I said with an array of size 13, with handling collisions using double hashing, insert the following keys. So this is what I asked you to do. And I want you to give me the resulting array. So I say, well, first hash 18. Well, here's a little table to help you. Your k is 18. The first hash function gives you a 5. Okay, so we stop there. We then put it in index 5. So 18 will go in index 5. We look at the next one, 41. 41, we hash it using the first hash function, we're going to get 2. So we put 41 in 2. Then we get 22. 22, we simply, we hashed it with the first hash function, we get 9. No collision so far. We're going to put 22 at position 9. 44. We go to 44, hash it. We got a collision. We know because from our table we can see that it happened before. But let's have a look, just in case your table is not convincing. We go to index 5, we see, we got 18 there, we can't put 44 there. So what do? Well, we put 44 in our second hash function, and our second hash function hashes it to 5. So we add the results from the first hash function to the second hash function, and we get a 10. And that's where we're going to probe. So we go to 10 and we see there's nothing there. So we put in 44. Then 59. We go to 59. We hash 59. Using the first hash function, we get 7. We see, well, there hasn't been anything probed to 7. So we go to 7. We see there hasn't been anything probed to 7. So we can put 59 in 7. Then we go to 32. Well, 32, the first hash function probes to 6. So we go look in 6. And we see it's empty. So we put 32 in 6. Then 31. 31. We use our first hash function, we get a 5. We can't because 18 is hashed to 5. So we need to probe again. So we do it. We do the second hash function, which gives me a 4. So we add 4 plus 5 is 9. And we're going to now look at 9. But we can't because 22 was hashed to 9. See? We can't. So what do? Well, all we got to do is say h of k plus d of k plus d of k, which gives us 13. So 5 plus 4 plus 4 is equal to 13. 13 is the size of the array. So 13 modulo 13 is 0. And that's where the 0 comes from. So we're now going to probe 0. And there's nothing there. So we can put out 31. The last is 73. 73, our first hash function gives us an 8. We look in 8. It's empty. So we can put 73 in here. Yeah, so this is how you would handle collisions using double hashing. And this is different from linear probing. You can easily see the difference. But a lot of thought needs to be put into devising our DFK, because our DFK needs to be able to traverse the list in a unique way, to allow us to store things and try to distribute our keys as evenly as possible, because that's our goal. So this last slide just talks about computational complexity. Now we could be harsh and we could say, in the worst case, we're going to be searching and inserting and removing in a hash table is O(n). But we can actually show that if we do pick our hash tables, if we do pick our hash function, which includes picking the hash code in the compression function, in a way that allows an even distribution, a uniform distribution of the keys over the hash table, then we can achieve O(1) for all of these things: for insertion, for erasing, for inserting, erasing, and the other one. So this is very important as searching. Yeah. So this is very important, right? So if you pick your hash table, your hash code and compression function in a sloppy way, then you would get this computational complexity. But if you're smart about it, and if you put a lot of thought into it, and you can actually and you empirically test other ways and design choices, you can achieve O(1), and this is very possible. You can show it's possible. You are using some heuristics. On average, you can get O(1). Something to keep in mind is the load factor when you're busy designing hash tables. You've got to take into account the number of keys and the size of the hash table, the ratio there. Okay, the number of keys, it's expressed as small n, and then big N is the size of the table. And the reason for this is because, remember, the larger the array and the smaller the keys, the greater probability of it being dispersed uniformly. If you have a very small cramped up space and you're trying to fit a lot of things in it, you're going to be able to fit them in less ways, which increases collisions. So just conceptually, having a small load factor is a good idea. And so so that's what we hash tables are used everywhere. They're used in most important problems in databases where we want to distribute keys. I think Facebook still uses hash tables to store friend lists and things like that. This is a very powerful technique. I invite you to read up more about it if you're interested. If you have any questions, feel free to post them on the forum on Moodle. Thank you.